Today I'm going to be talking to you about the acid-catalyzed ester hydrolysis video. I'm going to label one R group as just with an orange highlighter, and that R group is going to stay the same throughout the entire process. And then the other R group that is bonded to the oxygen in the ester, we're going to make it a methyl group just for the purpose of this video. So since this is ester hydrolysis, the reaction is going to be carried out with the addition of water and an acid. And for the purpose of this video, the acid that we're going to do is the hydronium ion. Now for the products that we're going to reach at the end is going to be a carboxylic acid and an alcohol. So we have the products and then we have the reactants. So this is going to be our general equation, and we have to figure out how did it go from point A to point B. So Chatellier's principle is applied in this reaction, which states that all reactions should be at an equilibrium. And since the ester is in water, hydrolysis is going to occur. One more thing to notice would be that this is the exact reverse of the Fischer esterification as well. So there are basically 6 parts to this. Before we get started, we want to know at which site the ester is going to be protonated. It could be on either of the oxygens. So we take hydrogen from our hydronium ion and see which cation would be better stabilized in the ester. As you can see, when we attach the hydrogen to the oxygen that is double bonded with carbon, there is a resonance structure which delocalizes the positive charge. So therefore, it would be a better alternative rather than attaching the hydrogen to the oxygen that is attached to the R prime group. So the first step would be to attach the hydrogen to the oxygen that is double bonded to the carbon. And now we have a protonated ester where we see the positive charge on the oxygen. And now since that positive charge is on that oxygen, the carbon has become more nucleophilic, making it more likely to be attacked by the water. So now the electrons on the oxygen molecule will be attacking the nucleophilic carbon. This makes our tetrahedral intermediate, but we still have a positive charge, so right now it is the conjugate acid of our tetrahedral intermediate. To get rid of that positive charge, to get the neutral form of our tetrahedral intermediate, the oxygen is going to accept the electrons from the hydrogen, while the hydrogen is going to go attach itself to the water, becoming a hydronium ion. Now we finally have our tetrahedral intermediate. Now we want to move on to steps 4 through 6. So the electrons on the oxygen that is bonded to the methyl group attracts the hydrogen on the hydronium ion, and then that becomes the conjugate acid of the tetrahedral intermediate once again, which gives the oxygen that is now bonded to the methyl group and the hydrogen a positive charge. Now, in order to lose the positive charge, the electrons from the bond with carbon are going to go back to the oxygen. This is what we call a good leaving group, as it wants to get the electrons back from the carbon, thus leaving our initial ester. So while that is happening, the oxygen that is bonded to the hydrogen is now going to form a double bond with our carbon. And when that occurs, that oxygen also becomes protonated, giving it a positive charge. The products in our step 5 are the protonated carboxylic acid and the methanol. And for the final steps, hydrogen is going to give the electrons to the oxygen as it has a positive charge, and the electrons from hydrogen are going to go to the water, making it a hydronium ion. And that is how acid-catalyzed ester hydrolysis occurs. Thank you.